Before we move to the used car dealer problem, we're going to review all of the rules about random variables and operations of random variables. First of all, just to remind you, this E stands for expected value, variance, standard deviation. Expected value is another name for the mean. If we add a constant to a random variable, it's the same as we add that constant or add or subtract that constant to the expected value. But adding only shifts a distribution. It doesn't affect its variability at all, its stretch. So there is no change to variance or standard deviation when we merely add a constant. Now if we multiply by a constant, it does stretch the distribution, spread it out more, or shrink it one way or the other. So it affects both the mean and the standard deviation. So we would multiply the expected value or the standard deviation by that constant. Now the variance, since the variance is the square of the standard deviation, which I forgot to mention up here, but the variance is standard deviation squared. So if we take the variance of constant times x, that's the same as the standard deviation squared. If we follow along what we did in the previous example and square everything, notice that we end up with c squared times standard deviation of x squared, which is c squared times the variance of x. So when we multiply by a constant, it directly affects expected value and standard deviation, but we multiply variance by the square of that constant. A little bit different. Now here's where we really run into some new things that that is the real gist of chapter 16, and that is adding or subtracting two random variables. Two occurrences of something that's a random process, or you could have several occurrences of the same random variable or two or more different random variables. When we add or subtract random variables, we add or subtract their expected values. Pretty straightforward. When we add or subtract random variables, we only add their variances. So variances add, expected values add or subtract. The reason the variances add is because no matter what type of process, adding or subtracting, we do, every time we do something random, it increases the variability. It's kind of like every time you round in math and do another step, it increases the error. It increases the variability every time we do a process, whether or not we add it or subtract it. Now standard deviation has to be handled a little differently. Standard deviation is the square root of variance. So if we take the square root of the variance of x plus the variance of y, that's the same thing as taking the square root of the standard deviation squared of x plus the standard deviation squared of y. So this is our rule for combining the standard deviations of two or more random variables. We cannot add them or subtract them directly. We always add their squares and then take the square root of the whole thing. Since that looks like the Pythagorean theorem, we refer to that, or our author refers to that, as the Pythagorean theorem of statistics. Now we're going to apply these rules to the used car dealer problem. So if we want to look at the used car dealer problem here, let's look at the first example here. Suppose the used car dealer runs autos through a two-stage process to get them ready to sell. The mechanical checkup costs $50 per hour and takes an average of 90 minutes. Since we're talking about cost per hour, I'm going to change 90 minutes to 1.5 hours with a standard deviation of 15 minutes or 0.25 hours. The appearance prep, wash, polish, etc. costs $6 per hour and takes an average of 60 minutes or 1 hour with a standard deviation of 5 minutes, 1/12 of an hour. Both the mechanical checkup time and the appearance prep time vary according to a normal model. So we're going to write down all of here's all of our given information from the chart, and we're going to say what is the question is, what are the mean and standard deviation of the total expense, and I'm going to use C, cost, to represent total expense, to prepare a car. And we're going to let M stand for mechanical time and A stand for appearance prep time and T stand for total time. Only I don't think I used T in this particular example. So the cost is $50 times the amount of time it takes to do the mechanical prep, since that's $50 per hour. So M is in hours, and 6 times the appearance prep in hours. So the expected value of C, well, we know that if we multiply by a constant, well, let's just go ahead and do this. The expected value of the cost is the expected value of 50M plus 6A. Well, we know that if we add two random variables, we add their expected values. If we multiply by a constant, we multiply the expected value by a constant. So it's just 50 times the expected value of M plus 6 times the expected value of A. 50 times 1.5 plus 6 times 1 equals $81. Okay, so this is the 1.5 hours. That's our expected mechanical prep time. Our expected appearance prep time is 1 hour times the amount of money per hour, $81. Pretty straightforward. Now the standard deviation, however, remember we can't add them in a straightforward way. We have to realize that we're dealing with variance, and so we have to use that standard or that Pythagorean theorem of statistics. So we know that standard deviation is the square root of variance. So we start with that. We know that variances add, so we went to this part. Then we know that the variance is the square of standard deviation. So this is standard deviation squared of 50M plus standard deviation squared of 6A. Well, we know that the standard deviation of 50 times M is just 50 times the standard deviation of M. So that's 50 times 0.25, which is the standard deviation for the mechanical prep time, 15 minutes. The whole thing squared, and 6 times 1/12, which is the expected value for, or the standard deviation for the appearance prep time, 1/12 of an hour, 5 minutes, and then we square that and we get 1251. Now this one's kind of messy right in here, so let me show you another way to approach number 1, and that's by doing something else first. So let's take a look at this example here. In this case, I wrote down all of the same given information, but instead of proceeding directly from here, then I did an intermediate step. I said, let's figure out the cost, and the expected value and the standard deviation of the cost for mechanical prep time and appearance time. So what I did was say that the expected value of the cost of the mechanical prep time, so I put C sub M as the cost of mechanical checkup, is 50 times 1.5, which is 75. The standard deviation of the cost of the mechanical prep time, mechanical checkup, is 50 times 0.25 or 1250, because I know that these are just being multiplied by a constant, so I can just multiply both the expected value and the standard deviation by a constant. Then I did the same thing for the appearance prep time. Mean and standard deviation of the appearance prep time times $6 per hour, and there's our mean and standard deviation of the cost. Then the expected value of the total cost, C sub T, is just adding together the two expected values. And then the standard deviation is the square root of 1250 squared plus 0.5 squared, which is the Pythagorean theorem of statistics, using squaring each standard deviation, adding them together, and taking the square root. Notice you get exactly the same thing as we did before. So either way, if one makes a little more sense to you than the other, that's fine, but either way works. Now, just to look at number 2. Number 2 says, what are the mean and standard deviation of the difference in cost for the two phases of the operation? Well, notice all we do is subtract expected values, but we still add the variances. Remember, these are standard deviation squared, so these are variances. We still add them because whether or not there's still the same amount of variation in these two processes, so when we combine them, we're still combining their variation. Even though we're combining them in a different way, we're still increasing the amount of overall variation. Now I'm going to stop here and you put example number 3 on a separate video.